Okay, so for all you philosophy enthusiasts out there, today we're taking a deep dive into the world of one very fascinating figure, Hermann von Helmholtz.
Now, Helmholtz was a true 19th century polymath. We're talking 1821 to 1894. And he wasn't just some armchair theorist. This guy made serious contributions to physics, the hard sciences.
Yeah, like he's the one who formulated the principle of energy conservation.
Precisely. He also did groundbreaking work on vortex equations, free energy.
Oh, and we can't forget about the ophthalmoscope.
Ah, yes, the ophthalmoscope, a practical invention with real-world impact. But here's the thing. He didn't stop there. Helmholtz was deeply engaged with some pretty fundamental philosophical questions, too.
Questions that are, like, right at the core of epistemology, the philosophy of science.
How do we actually perceive the world? What's the nature of space? Can we really know anything for sure?
Exactly. And he tackled these questions not as some abstract afterthought, but as an integral part of his scientific investigations.
Right, it wasn't just philosophizing for the sake of it. It was very much intertwined with his scientific worldview.
So for our deep dive today, we're focusing on Helmholtz's ideas, specifically for a philosophical audience, right?
Yeah, think of this as like a philosophical lens on Helmholtz's work.
And our main source material is the Stanford Encyclopedia of Philosophy entry on Helmholtz.
Which I have to say is a very comprehensive and scholarly overview of his life and thought.
Yeah, it really covers it all. So our mission here, for those who are into philosophy, is to really extract the most philosophically juicy bits of Helmholtz's work.
Especially his theories of perception.
Right, his ideas about geometry.
And of course, his overall epistemological framework.
His big picture view on knowledge and how we acquire it. And we'll also be keeping a close eye on how he engaged with, well, the dominant philosophical currents of his time.
Especially Kantianism.
Yeah, Kant was a huge influence on Helmholtz, though the extent of that influence is still debated. But that's a discussion for later. Let's start with how Helmholtz tackled the problem of perception, how we experience the world around us. Now, his predecessor, Johannes Müller, proposed what's known as a projection theory of perception.
Right, Muller's idea was that, there's this relatively straightforward causal pathway from stimulus to sensation. You get poked with a needle, you feel pain, light hits your retina, you see.
But then he ran into some problems, right? Like, what about binocular vision?
Exactly, binocular vision. Two slightly different retinal images somehow fuse into a single percept.
Right. So to account for these complexities, Müller came up with the law of specific sense energies.
The idea here is that each nerve fiber is inherently specialized.
Like hardwired to transmit a certain kind of sensory information, no matter what stimulus actually activates it.
So it's not about the stimulus itself, but about the specific nerve that gets triggered. It's like, different wires carrying different signals.
Okay, that makes sense. But then Müller tried to connect this idea to Kant's concept of pure intuition, specifically related to the retina.
Ah, yes, the Kantian connection. That's where it gets tricky. Because as the Stanford Encyclopedia entry points out, scholars like Robert Dessau have questioned whether this was even a legitimate interpretation of Kant.
Okay, so maybe not so Kantian after all, but the key takeaway here is that Müller believed in a fairly direct link between stimulus and sensation.
Right.
Yeah.
With some refinements to account for the complexities of how our senses actually work.
Now, this is where Helmholtz comes in and, completely revolutionizes our understanding of perception with his sign theory. So can you explain what he meant by signs in the context of perception?
Well, imagine this. Think about language. The word tree doesn't look anything like a real tree, does it?
Not at all. It's just a bunch of letters arranged in a specific way.
Right. But somehow, it still manages to convey the concept of a tree.
So it's like a symbol that stands in for the real thing.
Exactly. And that's essentially what Helmholtz was saying about our sensations. They're not direct copies of the external world. They're more like signs, symbols that represent those stimuli.
Okay, so our brain doesn't just passively receive information, it actively interprets it based on these sensory signs.
Precisely.
And this interpretation process is where his famous concept of unconscious inferences comes into play.
Right. The idea is that our minds are constantly making these little deductions, these inferences, without us even being aware of it.
It's like our brain is doing all this behind-the-scenes work to construct a coherent picture of the world.
And Helmholtz argued that this unconscious inference process is based on our past experiences, our learned associations.
So it's not just about the raw sensory data, it's about how our brain interprets that data based on what we've already learned.
Precisely.
Can you give us an example of how this unconscious inference might work in practice?
Sure. Take, for instance, our perception of spatial location, where things are in space.
Yeah, that seems pretty basic, like I just see where something is.
Right, but Helmholtz argued that it's not that simple. Our eyes only receive two-dimensional images on the retina.
Right, but we experience the world in 3 dimensions.
Exactly. So how do we get from those flat retinal images to a three-dimensional understanding of space?
That's where the unconscious inferences come in.
Right. Helmholtz said that we learn to infer spatial relationships from various cues, like stereoscopic vision.
The fact that we have 2 eyes, each seeing the world from a slightly different angle.
Exactly. And things like linear perspective.
Ah, like how parallel lines seem to converge in the distance.
Precisely. These are all visual signs that our brain has learned to interpret to infer depth in spatial relationships.
Okay, that's fascinating. So our perception of space is not just something that's given to us directly, it's something we actively construct.
And it's happening all the time without us even realizing it.
Now, the Stanford Encyclopedia entry also mentions the influence of another philosopher, Hermann Lotze, and his concept of local psyche.
Local tychen or local signs. This idea is really crucial to understanding Helmholtz's theory of spatial perception.
So what are these local signs?
Well, Lotzer proposed that each sensory nerve ending has a kind of unique tag associated with it, a local sign that indicates its position.
Okay, like a little GPS coordinate for each nerve ending.
Yeah, that's a good way to think about it. And we learn the spatial significance of these tags through experience, through our interactions with the world.
So, for example, if I touch something with my fingertip, the specific nerves that are activated tell me not only that I'm touching something, but also where on my fingertip I'm being touched.
Precisely. And Helmholtz took this idea further, suggesting that the entire field of our perception acts as a kind of generalized local psyche.
Okay, so it's not just individual nerve endings that have local signs. It's like our entire perceptual space is a kind of map.
Exactly. A map where the relationships between the parts, the spatial relationships, are learned through our experiences.
So what we perceive as the external world is actually this internal constructed model based on these local signs.
That's the key insight of Helmholtz's sign theory. We don't directly apprehend the qualities of objects out there in the world.
Like color, for example.
Right. For Helmholtz, the redness of an apple isn't an intrinsic property of the apple itself.
It's a quality generated by our nervous system in response to certain wavelengths of light.
And the way we spatially organize those qualities, the redness here, the greenness there, that also comes from our experience, from consistently encountering sequences of sense impressions.
He uses the example of grasping a pen, right?
Yeah, each part of our hand feels the pen differently. But we don't perceive it as multiple objects. We perceive it as a single pen with a specific shape and size.
Because our brain has learned to integrate those sensations into a coherent whole.
And that integration relies on our knowledge of our own body, our hand in this case, and the inferences we've made based on past experiences.
So even our understanding of spatial distinctions like depth is not innate, it's learned.
Right. The Stanford Encyclopedia entry even mentions how some scholars, like Lenoir, have argued that Helmholtz's concept of unconscious inference is a way of operationalizing Kant's ideas.
Okay, so maybe there's a Kantian connection there after all. But it's not a direct mapping. It's more like Helmholtz took Kant's ideas and grounded them in a very specific physiological and psychological framework.
Exactly. He made them concrete, empirically testable.
And this brings us to the famous debate between Helmholtz and Ewald Hering about the nature of spatial perception.
Ah, yes, the Helmholtz-Hering debate. This was a clash between nativism and empiricism.
So for our philosophy fans, can you briefly explain the difference between nativism and empiricism?
Nativism is the view that certain kinds of knowledge or cognitive abilities are inborn, innate, part of our biological inheritance.
Like we're born with them pre-programmed, so to speak.
Right. Empiricism, on the other hand, emphasizes the role of experience, of learning from our senses and interactions with the world.
Okay, so in the context of spatial perception, Hering, the nativist, argued that our perception of space, especially depth, is largely innate.
Like, it's just part of how our brains are wired.
Whereas Helmholtz, the empiricist, insisted that it's primarily learned through experience.
Through the interpretation of those sensory signs we talked about.
And the horopter problem became a key battleground in this debate. Can you explain, in simple terms, what the horopter problem is all about?
Sure. When we focus on a point in space, There's a particular region called the horopter where objects stimulate corresponding points on our two retinas.
So we see those objects as single, not double.
Right, but objects that are closer or farther away from the horopter stimulate slightly different points on the retinas.
Which should, in theory, lead to double vision, but it doesn't always.
Exactly. So the question is, how does the brain resolve these disparate retinal images into a single unified spatial percept?
And this is where Helmholtz and Herring differed in their explanations.
Helmholtz argued that this resolution is achieved through unconscious inferences, through learned adjustments based on our past experiences.
Like, our brain learns to compensate for those discrepancies between the two retinal images.
Right. He uses the analogy of shaving in front of a mirror. When you first try it, it feels really awkward.
Yeah, because your movements in the mirror are reversed.
Exactly. But you eventually learn to adjust, to coordinate your movements correctly.
And that adjustment, for Helmholtz, is a prime example of unconscious inference.
It's a learned skill, not an innate one.
So for Herring, the resolution of the horopter problem was more like an inherent capacity that simply matures over time.
Like walking or talking.
Whereas for Helmholtz, it was a skill honed through practice and experience.
And as the Stanford Encyclopedia entry points out, this disagreement wasn't just about the mechanics of perception. It had broader philosophical implications.
Because it touches upon the fundamental question of how we acquire knowledge.
Exactly. Helmholtz's sign theory, with its emphasis on unconscious inferences, implies that our access to objective reality is indirect.
We don't just see the world as it is, we see it through the lens of our learned interpretations.
And those interpretations might not always be accurate.
Right. It's like we're always looking at the world through a kind of filter.
Whereas Herring, with his nativist view, suggested a more direct and immediate apprehension of spatial reality.
So it's a debate about the nature of reality itself and how our minds connect to it.
And it's a debate that continues to resonate with contemporary philosophy and cognitive science.
Now, for a philosophical audience, the question of Kant's influence on Helmholtz is crucial. But, as we mentioned earlier, there's no clear consensus on this.
Yeah, it's one of those scholarly debates that seems to go on forever.
Some scholars, like Galati, Pastor, Leary, and even the neo-Kantian Alois Riel, see a very strong Kantian influence in Helmholtz's work.
They point to his emphasis on the active role of the mind in shaping perception, which aligns with Kant's transcendental idealism.
Right, the idea that our minds impose certain categories and structures on our experience. But then others, like Hatfield, Boring, and even Ernst Cassirer in his later work, argue that Helmholtz's commitment to empiricism, to learning from experience, ultimately diverges from Kant's core tenets.
Especially the idea of synthetic a priori knowledge. Knowledge that is both independent of experience and yet informative about the world.
So it seems like there's a case to be made for both sides. Maybe a mixed reading is the best approach, acknowledging both the Kantian influences and the significant departures from Kantianism in Helmholtz's thought.
It's definitely a complex issue with no easy answers.
And then there's the question of Fichte's influence, which is less prominent in the literature but still worth considering.
Some scholars, like Heidelberger and de Kock, have drawn parallels between Fichtean idealism, particularly the subject-object dialectic, and Helmholtz's analysis of perception.
But Hatfield, who we mentioned earlier, argues against a strong Fichtean influence, suggesting that Helmholtz's primary intellectual debts were to empirical physiologists like Müller and Wundt.
Which, in his view, led Helmholtz to adopt a kind of modest realism.
Meaning that while our perceptions are constructed, they still reflect certain aspects of the real world.
Right. It's not pure idealism where the mind creates reality. There's a connection, however tenuous, between our internal model and the external world.
Now, here's where it gets really interesting for contemporary philosophy. The Stanford Encyclopedia entry connects Helmholtz's ideas to the predictive processing paradigm in modern neuroscience. Can you unpack that for us?
Sure. The predictive processing framework, which has become very influential in neuroscience and cognitive science, basically argues that our brains are constantly making predictions about the world.
Like based on our past experiences and current context.
Exactly. And we use these predictions to anticipate what's going to happen next, to make sense of the incoming sensory data.
And if there's a mismatch between our prediction and the actual sensory input, we update our model.
Right. That's called a prediction error.
And this process of prediction and error correction is happening all the time, unconsciously.
And Helmholtz's concept of unconscious inferences can be seen as a precursor to this idea. He was already talking about the brain as a kind of prediction machine, making inferences about the causes of our sensations.
So it's like Helmholtz anticipated some of the key ideas of modern neuroscience.
And the connection is even more explicit in the field of machine learning. Early computational models of predictive processing were actually called Helmholtz machines, directly referencing his influence.
It's amazing to see how these 19th century ideas are still shaping cutting-edge research today. And then there's the relationalist reading of Helmholtz's theory of perceptual properties, which also has connections to Kant and contemporary philosophy of perception. Can you elaborate on that?
So the relationalist view, as championed by philosophers like Allais and Tratz, argues that what we perceive are not intrinsic properties of objects, but rather relationships between objects and our sensory system.
So, like, the redness of an apple isn't a property inherent in the apple itself.
It's a product of the interaction between the apple, the light reflecting off of it, and our visual system.
It's a relational property. And this view has been connected to certain interpretations of Kant's transcendental idealism, which also emphasizes the relational nature of our experience.
Right. The idea that we don't have direct access to things in themselves, only to how they appear to us, filtered through the categories of our understanding.
And this relationalist perspective is very much alive in contemporary philosophy of perception, particularly in discussions of color, sound, and other sensory qualities.
Patton, who we mentioned before, adds an important nuance to this reading of Helmholtz. He argues that, for Helmholtz, these relational properties are not fixed or absolute.
They can change based on our experiences.
Right. Through habit and repeated exposure, our perceptual systems can adjust, leading to changes in how we experience those relational properties.
So it's a dynamic and flexible system, not a static one.
Precisely.
Before we move on to Helmholtz's groundbreaking work on geometry, let's briefly touch upon his contributions to color theory.
Ah, yes, color theory. Helmholtz was a pivotal figure in developing our modern understanding of color vision.
Yeah, he was really one of the pioneers in this field. What were some of his key insights?
Well, for one, he defined what's considered the first non-Euclidean line element in color space.
Okay, for our philosophy listeners who might not be familiar with that, what is a non-Euclidean line element?
It's a mathematical way of representing the relationships and perceived distances between different colors. And it's non-Euclidean because it doesn't follow the rules of classical Euclidean geometry.
So it's like a different kind of geometry specifically applied to the perception of color.
Exactly. And Helmholtz's work in this area laid the foundation for later developments in color science.
It's amazing how he could move seamlessly between these different fields: physiology, psychology, physics, mathematics.
He was truly a polymath, able to synthesize knowledge from different domains and apply it in novel ways.
Okay, so now let's dive into Helmholtz's foray into the world of geometry. It's quite surprising, actually, that someone so deeply immersed in physiology would make such profound contributions to geometry, a field that seems, well, more abstract.
It might seem surprising, but as the Stanford Encyclopedia entry points out, even within his physiological research, Helmholtz always had this mathematical mind. He was trained as a physicist, and his inclination for mathematical reasoning was always present.
Yeah, you can see it in the way he used mathematical models to explain physiological phenomena.
Precisely. And his early work on perception, on how we perceive spatial relationships, actually laid the groundwork for his later explorations of geometry.
So it wasn't a complete break. It was more like a natural progression of his interests.
Exactly. He was always fascinated by the connection between our subjective experience of space and the underlying mathematical structure of reality.
And then in 1868, he kind of burst onto the geometry scene, surprising a lot of people in the academic world. What sparked this sudden interest in geometry?
Well, it wasn't entirely sudden. Remember, his initial ambition was actually in physics.
Right, and he always kept up with the latest developments in mathematics and physics.
And one of the most groundbreaking developments in 19th century mathematics was Riemann's 1854 Habilitations read on the foundations of geometry.
Which, for our philosophy enthusiasts, was a very influential lecture that challenged the long-held assumption that Euclidean geometry was the only true geometry.
Right. Riemann proposed that the geometry of space could actually be determined by empirical measurement, not just by a priori reasoning.
So it was a radical departure from the traditional view of geometry.
And Helmholtz immediately recognized the significance of Riemann's work. In fact, he even claimed to have independently arrived at similar conclusions, though he readily acknowledged Riemann's priority.
So it was like they were both thinking along the same lines, but Riemann got there first.
And Helmholtz's 1868 lecture and subsequent essay on the facts underlying geometry were his way of engaging with and contributing to this new Riemannian perspective.
The title itself suggests a shift in focus, from abstract axioms to the empirical facts that might support or refute those axioms.
Exactly. It's a very empirical approach to geometry, which aligns with his overall emphasis on experience as the foundation of knowledge.
Now, Riemann's focus was largely on the topological properties of space. Can you explain what topology is in simple terms?
Imagine you have a rubber sheet. You can stretch it, bend it, twist it, but you can't tear it or make any holes in it.
Right.
The properties of that sheet that remain invariant under those transformations, like the number of holes, for example, those are topological properties.
So topology is about the fundamental connectedness and shape of space, regardless of its specific measurements.
Precisely. And Riemann was interested in how we could determine the topology of space itself, not just of individual objects.
But Helmholtz took a slightly different approach to geometry. He was more interested in the metric properties of space.
Right. Metric properties are about distances, angles, the things we measure.
So while Riemann focused on the overall shape, Helmholtz wanted to understand how we could measure space consistently and reliably.
And this led him to the concept of rigid motions as a fundamental principle in geometry.
Okay, so what are rigid motions?
Think of moving a solid object around in space without changing its shape or size.
Like sliding a book across a table, rotating a cube.
Exactly. Those are rigid motions. They preserve the distances between all the points in the object.
So the book doesn't suddenly shrink or expand when I move it.
Right. And Helmholtz wanted to understand what geometrical axioms are necessary for such rigid motions to be possible and for our measurements to remain consistent during those motions.
So it's about finding the minimal set of rules that allow us to measure space accurately?
Precisely. And his work in this area laid the groundwork for the later formalization of rigid motions using group theory by the mathematician Sophus Lie.
It's interesting how these different branches of mathematics are interconnected.
Yeah, it really shows how seemingly abstract mathematical concepts can have very concrete implications for our understanding of the physical world.
Now, the Stanford Encyclopedia entry mentions a fascinating episode where Helmholtz initially made a mistake in his arguments about geometry. Can you tell us about that?
Sure. So, in his early work on geometry, Helmholtz argued that only Euclidean geometry could account for the possibility of rigid motions and consistent measurement.
So he was essentially saying that Euclidean geometry was the only geometry compatible with our experience of space.
Right. But then the mathematician Eugenio Beltrami pointed out a flaw in his reasoning.
Uh-oh, what was the flaw?
Beltrami showed that a non-Euclidean geometry, specifically Lobachevskian geometry, could also be consistent with rigid motions and measurement.
How is that possible? I thought non-Euclidean geometries were, like, weird and distorted.
They are different from Euclidean geometry, but they can still be consistent with certain aspects of our experience.
So it's not like one geometry is right and the other is wrong. It's more like they describe different kinds of spaces.
Exactly. And Beltrami demonstrated this by constructing a model of Lobachevskian geometry on a surface called a pseudosphere.
What's pseudosphere?
It's a surface with constant negative curvature. It's kind of like a saddle shape. And Beltrami showed that on this surface, you could have rigid motions and consistent measurement, even though the geometry is non-Euclidean.
Wow, that's mind-bending. So Helmholtz's initial assumption that only Euclidean geometry could work was wrong.
And what's remarkable is that he immediately admitted his mistake. He didn't try to defend his position. He acknowledged the validity of Beltrami's counterexample.
That's a true sign of a great scientist, being willing to change your mind when presented with new evidence.
Exactly. And this openness to new ideas led him to write his later, very influential essay on the origin and significance of the axioms of geometry.
So in this later essay, he revised his views on geometry, right?
He went deeper into the question of how we come to have knowledge of geometrical axioms. He explored whether non-Euclidean geometries could even be visualized or intuitively grasped.
And what did he conclude?
Well, he didn't come to definitive answers. His essay was more about raising questions, exploring the philosophical implications of these new geometrical possibilities.
And his essay sparked a lot of debate among subsequent philosophers of science, right?
Oh, absolutely. Figures like Moritz Schlick and Hans Reichenbach, who were both major figures in the development of logical positivism, were deeply influenced by Helmholtz's work on geometry.
They grappled with the question of whether geometrical axioms are a priori truths, as Kant had argued, or whether they are ultimately based on empirical experience.
And even Bertrand Russell, in his early philosophical work, engaged with Helmholtz's arguments about geometry.
So Helmholtz's work on geometry really shook things up in the philosophical world. It challenged long-held assumptions about the nature of space and our knowledge of it.
And Biagioli's comprehensive book, Space, Number, and Geometry from Helmholtz to Cassar, provides a detailed analysis of this intellectual trajectory. He examines Helmholtz's theories in relation to figures like Kant, Riemann, Gauss, Klein, Lie, Poincaré, and the Neo-Kantians.
So it's a must-read for anyone interested in the history and philosophy of geometry.
And Neuber's work specifically analyzes Helmholtz's influence on Schlick's early philosophical development.
Now, what about the connection to Einstein's theory of relativity? The Stanford Encyclopedia entry briefly mentions that.
Right. Some scholars have argued that Helmholtz's emphasis on empirical constraints on geometry was a precursor to Einstein's theory of general relativity, which posits that gravity is not a force, but a curvature of space-time.
So instead of thinking of gravity as a force pulling objects together, we think of it as a warping of the geometry of space itself.
Exactly. And Giovanelli, in his work, argues that while the Helmholtzian tradition was influential, the Riemannian tradition played a more direct role in the development of general relativity.
So it was more of a convergence of these two traditions, rather than a direct line from Helmholtz to Einstein.
Precisely.
Finally, in the context of geometry, Helmholtz also made important contributions to the theory of measurement.
Right. He wasn't just interested in how we measure space, he was also interested in the philosophical foundations of measurement itself.
So he was thinking about what it means to measure something, what makes a measurement valid and reliable.
Exactly. And his essay, Über Zählen und Messen, on counting and measuring, is considered a pioneering work in this area.
So what were some of his key insights in this essay?
He explored the conditions under which we can meaningfully assign numbers to magnitudes. Like when we say something is 5 meters long, what does that actually mean?
Right. It seems straightforward, but there's a lot of philosophical depth to it.
And he also investigated the relationship between counting discrete objects and measuring continuous quantities.
Like, how do we go from counting apples to measuring the length of a table?
Precisely. And his work in this area has been influential on later philosophers of science who have grappled with the nature of measurement, like Cantu, Neuber, and Biagioli.
So Helmholtz wasn't just a user of mathematics, he was also a philosopher of mathematics.
He was thinking about the big questions about the nature of mathematics and its relationship to the physical world.
Okay, so now let's move on to the third major area we want to cover today. Helmholtz's epistemology, his overall theory of knowledge.
This is where his philosophical ideas really come to the forefront.
And the Stanford Encyclopedia entry highlights the 1921 edition of Helmholtz's epistemological writings, edited by Paul Hertz and Moritz Schlick, as particularly significant.
These editors saw Helmholtz as a key figure in the development of modern scientific epistemology.
And Schlick, in particular, interpreted Helmholtz as a kind of anti-Kantian.
Right. He argued that Helmholtz's work on the foundations of geometry and measurement undermined Kant's doctrine of a necessary a priori.
So, for Kant, certain kinds of knowledge, like our knowledge of Euclidean space, were thought to be both independent of experience and yet informative about the world.
But Helmholtz, according to Schlick, showed that even our understanding of space is ultimately based on experience, on our interactions with the world.
And this anti-Kantian reading of Helmholtz is also discussed by de Salle, who we mentioned earlier.
And it's interesting to note that even in modern physics, the methods used to derive the space-time metric in general relativity have been compared to Helmholtz's approach to geometry.
So his ideas continue to resonate with contemporary physics as well. But here's where it gets even more philosophically interesting. Despite Schlick's anti-Kantian interpretation, Helmholtz's concept of the a priori has actually inspired new readings of Kant.
Right, particularly through the work of Hans Reichenbach, who, like Schlick, was a major figure in logical positivism.
So how did Reichenbach reinterpret Helmholtz's concept of the a priori?
Well, Helmholtz talked about the a priori in space as the manifold of possible orientations.
Okay, that sounds pretty abstract.
It is, but essentially he was suggesting that there are certain structural features of space that are not determined by experience, but are necessary for us to have any experience at all.
So it's like a framework that makes experience possible, but the specific content of that experience is filled in by our interactions with the world.
Right, and Reichenbach argued that this view could actually be reconciled with a more nuanced reading of Kant's transcendental idealism.
So it's not a complete rejection of Kant, it's more like a reinterpretation, a way of making Kant's ideas compatible with modern science.
Exactly. And both Schlick and Reichenbach recognized the important intellectual relationship between Helmholtz and Poincaré, though they differed in their assessments of Helmholtz's conventionalism.
And even Michael Friedman, a contemporary philosopher of science, has been influenced by Helmholtz's ideas, particularly through the lens of de Salles' scholarship.
So Helmholtz's legacy is very much alive in current philosophical debates.
The Stanford Encyclopedia entry also mentions how Helmholtz's concept of sensation spaces influenced a wide range of thinkers, including Boltzmann, Poincaré, Carnap, Russell, and Weil.
Yeah, his ideas about the relationship between the structure of our sensory experiences and the philosophical understanding of space and perception had a major impact on 20th century philosophy.
And scholars like David Heider and de Kock have traced these intellectual lineages in detail.
And Biagioli, who we mentioned earlier, has also examined Helmholtz's often overlooked debate with Carl Christian Friedrich Krauss, focusing on their contrasting views on the status of geometrical axioms.
And Derrigel has provided a rich historical context for Helmholtz's theories of number and measure, situating them within the broader intellectual landscape of the 19th century.
So there's a wealth of scholarship exploring the impact of Helmholtz's ideas on subsequent philosophical thought.
And then there's Schemann's perspective, which frames Helmholtz's work as a kind of turning point in the history of science and philosophy.
Right. Schemann argues that Helmholtz represents a shift towards a more modern scientific tradition, one characterized by relativization of claims to validity and a loss of certainty.
So it's a move away from the quest for absolute truth and towards a more provisional, fallibilistic understanding of knowledge.
Exactly. Scientific claims are always subject to revision in light of new evidence and theoretical developments.
Which is, of course, the hallmark of modern science. We're always refining and updating our knowledge.
And Helmholtz, according to Schemann, was a key figure in this transition to a more modern scientific worldview.
Now, here's a fascinating connection that the Stanford Encyclopedia entry mentions. Helmholtz's sign theory of perception is seen by some as having an indirect influence on Wittgenstein's picture theory of meaning. Can you explain how that connection works?
It's a bit of an indirect connection, but it goes through Heinrich Hertz, who is a physicist and philosopher of science.
Right.
Hertz, along with Boltzmann, developed what's known as a picture theory, where scientific and linguistic theories are seen as representations or models of the world.
So, like, our theories are like pictures that try to capture the structure of